Hi, Assalamualaikum. For this video, we continue for the chapter 1, simple harmonic motion, but with a pendulums. Okay, so pendulum, we have one string connected to the bob, okay, which have weight. So the string will be in length, certain length that we can measure. So what we can count from here, actually, we can get the value, the period for the one cycle. So for the pendulum, one cycle means, okay, I need to stop back, okay. Starting point here, okay, that's one cycle. Okay, so when it's from the starting point, move and moving back to the when the origin, that will be counted as a one cycle. And for the experiment, we can measure the period needed for the one cycle. But for the pleasure for get the accurate calculation, we need to do 10 oscillation and to get the one of the period. So we can release this and count as 1, 2, 3 until 10, and then we can measure the period. From there we can calculate by divide by 10, then finally we can get the period for the one cycle, and we can find the frequency. So later on we can calculate using the mathematical to prove the angular frequency for the pendulum, like what we have done before for the mass spring. For those who doesn't watch the mass spring, we can check from my channel, then it will help you to understand this. For pendulums, we have length L, okay, it's that string connected between the pivot to the ball, okay, the bob here, and connected to the bob with the certain mass. When we pull here from the starting point, then this pendulum will oscillate, will move to the left and back to the right as a one cycle. So this will be another example for the simple harmonic motion compared to another one which is mass spring system. So for drawing, okay, this is what we call as a the drawing for pendulums. So right now we have here with length L and also mass here, and then we have the angle theta, and the angle should be less or very small, okay, very small, so around 3 degree, okay, so that they can avoid a lot of the friction there. And for calculation, okay, we have another force here which is a tension force for the string. So we have a tension force that opposite to the motion force here, and for that we have here Ft cos theta mg. So for this Ft, we need to, okay, I just put some big angle here, so we need to split into x and y. Okay, so we have here for y axis, okay, because of this theta here, and this is will be Ft. Okay, so this area should be Ft sin theta, I suppose it, Ft sin theta, because sin theta you can get this value over Ft, so it means that this value is Ft sin theta, and for this one will be Ft cos theta, since it's similar with this area. Okay, cos means side over hypotenuse, so we have the this value Ft cos theta. So we have for what, this is for y axis, okay, and this one for the x axis, and for that we put this value, because of this y axis we have two value here, Ft cos theta and mg. So here we have Ft cos theta and mg, okay, Ft cos theta and mg. Since theta is very small, which is around 3 degrees Celsius, sorry, 3 degree, okay, so around 3 degree, what we can get here, the cos theta value is very small, so means that cos theta become very near to 1. Okay, since that the graph of the cos, okay, and because 3 degrees very near to 0, so the cos theta is very near to 1. So what we can have here is Ft is really near to the mg. Okay. And we have another one here which is for x-axis, okay, we have Ft sin theta, which is Ft is mg, and we have here another x-axis which is fx equal to ma, since it's the motion of the pendulum itself. So when we arrange, okay, because we have here for y-axis here we have ma, okay, the motion is equal to minus ft sine theta. Okay, since that we have here ma here, okay, and then we know from the x-axis, which is ft is very near to mg, so we have here ma equal to minus mg sine theta. Okay, and we can rearrange here. Okay, okay, this because we know that the acceleration is equal to double differentiation of x. Okay, dx over dt square. So we have here, which is this is ma, m d square x over dt square, and then plus we know that ft is mg sine theta equal to 0, and then we know that x sine theta is equal to x over L. How we get that? Okay, so again this pendulum, okay, this is a theta. Okay, so we know that this length is L, and this we put value x, so we got for sine theta is equal to x over L for the distance. Okay, so finally what we have here is m d square x over dt square plus mg x over L equal to 0, and we can cancel out m here. Okay, we can remove m here, so finally we can get the value this d square x over dt square plus g over L x equal 0. Oh, sorry. So this one is using the small l, and this one for the capital letter of L. This is the same thing. Okay. Same with the pendulum. For the mass-spring system, we try to find the value of the omega here, the frequency for pendulum. So we know that x is equal to a cos omega t, because this oscillate. So a will be the amplitude. Okay, the amplitude between, okay, the amplitude between this. Okay, this will be a. Okay, so this will be the amplitude. So differentiate a cos omega t, we can get the minus omega a sine omega t. Double differentiation, you can get here minus omega square a cos omega t, and because of a cos omega t is same with x, we have here minus omega square x, and we can put everything in this equation. Okay, so finally you can get here to replace the d square x over dt square is equal to minus omega square x. So we have minus omega square x, and then plus g over L x equal to 0, and then we rearrange to remove the negative. We have here omega square x plus equal g over L x. Okay, remove x because we have x for both. So finally what we have here, omega square. Okay, omega square is equal to g over L, or omega is equal to square root g over L. Again, to find the frequency, we know that omega is equal to 2 pi f and 2 pi over t period. So the frequency itself is 1 over 2 pi g over L, and the for period is 2 pi L over g. So we can using the put everything in the equation of motion first. Okay, so the equation for pendulum, d square x over dt square, dt square plus omega square x equal to 0, which is omega square is equal to g over L. So what happened to the pendulums? When we have a different length, okay, when we increase the length of the string, so we can get the period will be increased. Means that for smaller compared to the longer, okay, this one will have a longer period to complete a one cycle compared to this one. But we go to frequency, this have a higher frequency compared to this one. Okay, so the period low but the frequency high. Okay. So this one is a, we increase the period, the frequency will reduce. Sorry. So then this what we have for the pendulums. And how about the G? Of course we know that the gravity for the earth is constant. Okay, maybe if we change the gravity we are doing in the moon or everything, it will affect. So my question, how about mass? What happen if we use mass which is 2 times larger than the first one? Is it affect the period or the frequency? Maybe I let you to think. Okay, thank you, see you again, and bye.